for inviting me to deliver this talk in this MMAP 2020. So I'll be talking on highlight of nuclear physics experiment using DCC at Kolkata. So as you know, the Variable Energy Cyclotron Center Kolkata was set up by the Department of Atomic Energy, Government of India, with the objective to promote accelerator-based research in fundamental nuclear sciences as well as in multidisciplinary application areas in the country. Variable Energy Cyclotron was the first large accelerator developed completely indigenously by Indian scientists and engineers. Variable Energy Cyclotron recently completed its 40 years of operation in 2017. During the past 4 decades, variable energy cyclotron has been used extensively in exploring the properties of nuclei with the help of low energy light as well as heavy and accelerated beams. So, my presentation will be like this: VECC, the accelerator and its evolution, experimental infrastructure and its evolution, research activities, changing phases. Up to 2017, the whole work have been compiled in a review article, Europhysics JA 2018. So, I say that the presentation is only thematic and not chronological, highlight only major experimental achievements, citation only representative, not exhaustive. So the accelerator evolution of the beam, it was operational in 1977 and experiments were carried out using light and beams. Then PIG ion source have been replaced to provide heavy ion beam from ECR ion source, and experiments with light heavy ion beam was carried out. Then again in 2010, light ion beam was provided for experiments, and then again in 2018, heavy and light ion beam was delivered from new ECR ion source, and in 2019, again it was converted to provide light ion beam. Until now it is providing light ion beam. So, experimental activities evolution. Experimental activities followed facility development. First 2 decades, simpler experiment, mostly inclusive type of experiments were carried out, and next 2 decades, complex experiment setup involving many types of detector, exclusive measurements, multi-parameter measurements with complete event reconstruction, more detailed studies have been carried out. So this is the typical experimental facilities till 1977 to 1991. We have 3 beam line. One is beam line in cave 1. This line is mostly used for irradiation type of experiment, and there is a helium electrical separation facility as well facility upstairs. And then this line 2 in cave 2, this is used for there is a scattering chamber, and this scattering chamber is used for charge particle spectroscopy and fission fragment studies. This was an old picture. I think this barricade is not there, and in the beam hall 2 there are two lines. This line 3 is mostly used for in-beam gamma ray spectroscopic study. The detectors used were silicon surface barrier and silicon silly detectors made at VCC, gas ionization detector made at VCC, and then jelly HBT detector and sodium ion detector for gamma detection. So VCC startup journey first, internal beam June 16, 1977. External beam for experiment was obtained during 1980 to 81. First extracted beam and elastic beam scattering experiments were done using 36 MeV alpha on board, and the main aim of this experiment was to carry out beam energy determination and phenomenological to get the phenomenological optical potential parameters, and it has been published in Pramana. So next, this is the typical experimental snapshot carried out during 1978 to 2007, where from elastic scattering and transfer reaction, fission, quasi-fission studies, quasi-molecular resonances, complex fragment emission, GDR built on excited field, non-statistical gamma ray emission, particle-particle correlation, variation of beryllium-7 decay, gated gamma ray spectra from INGA, and GDR splitting and deformation, and many more studies have been carried out. So I must show this paper where our sir have participated in this experiment, heavy fragment emission in alpha-induced reaction on aluminum. So sir has taken the entire leadership also for this experiment. So this is the experiment where we studied the fragment emission in alpha-induced reaction on aluminum target, and different fragments have been identified using gas delta E silicon telescope, and the fragments cross-section have been explained using binary fragmentation, asymmetric to a binary fragmentation model. So now the experimental facilities from 2007 to until continuing. So these lines is mostly used for radiation damage studies by material science people, and other irradiation type of experiments by radiochemistry, analytical chemistry group, our group, and RIB group. They are using this line, and in this scattering chamber, nowadays we are using silicon steel detectors, the Marder detector for that particle spectroscopy, and MWPC type detector for fission dynamic studies. And this line is extensively used for in-beam gamma ray spectroscopy using Venus plus Venture array, Inga setup, and high energy gamma ray measurement using lambda array, and nuclear level density studies using neutron time of flight array, and angular momentum multiplicity by measurements by gamma multiplicity array. So moreover, we have made a 4-pi neutron multiplicity detector array. We are developing many other facilities. So major facilities developed or are being developed at PCC for nuclear physics experiment are charge particle detector array for kinematic reconstruction and analysis. This is a unique array developed for the first time in India, and it will be used mainly for superconducting cyclotron experiment. And we have made a neutron time of flight array consisting of 50 neutron time of flight detector. All are developed at BCC. These detectors are developed at BCC. We have Venus BCC array for nuclear spectroscopy, and Venture BCC array for nuclear fast timing and angular correlation array. We have multi-wire proportional counters. We have lambda array, large area modular VF2 detector array. We have segmented clover. We are developing this spinning trap facility. So a typical experimental setup at present are where in an experiment all the types of detectors have been used. You see neutron detector, large area modular VF2 detector array, silicon strip and scissor detector array inside the chamber, and this is the multiplicity filter. So how the complicated setup we are using at present. So moreover, nuclear structure studies using gamma ray spectroscopy, we had 2 campaigns of Indian National Gamma Array, phase 1 and phase 2. About 40 experiments are performed by users from all over the country in these 2 campaigns, and 11 journal publications, maybe 2 or 3 more. Exactly this number may change. So have been carried out, and recent campaign of multi-detector gamma array where this is a collaborative endeavor among SNP, UGC, CSR and Kolkata, that Inga support structure have been modified with a new mounting plate. Additional 2 position for global along with VGO and 4 position for lanthanum movement detector have been used. So this is the upgradation of Inga structure. So moreover, we are developing the penning trap facility, and the first trap signal at 4K have been observed recently for electron trapping of electron have been seen. And we have also a data acquisition system developed by our computer and informatics group, which we are using for our experimental cell. Without this, we will not be able to complete our experiment. So now let me come to the experiment. In nuclear reactions, in charged particle spectroscopy, we do fragment emission studies, fusion fission, diplastic orbiting, diplastic, quasi-elastic, etc. We studied transfer reaction, we studied deformation of nuclei using light charged particle as a probe, cluster structure studies, Hoyle state, other cluster state of carbon, Hoyle analog state and excited state of Hoyle analog state in other nuclei, effects of clustering in fragment emission. This is a typical experimental setup and this is a typical E-delta plot, and these are some of the recent publications using charged particle spectroscopy. So one of the experiments which carried out where survival or orbiting at a higher excitation. Orbiting is a phenomenon where instead of forming a compound nucleus, the target projectile combined to form a rotating dinuclear complex, equilibrated in all respects other than shape degree of freedom. So reactions studied were neon on carbon at 145 to 200 MeV, and so it has been observed that yield of the carbon and boron, there is a large enhancement of fully energy than yields of carbon and boron over the statistical model prediction. So they connected the contribution from non-statistical fusion channel and formation of a large deformed system establishing orbiting for the first time at such higher excitation energy. This, if it is an orbiting system, then these will have a larger radius. So such large deformation have been confirmed by alpha evaporation spectra from neon on carbon and neon on aluminum reaction. So you see a large value of R0 parameter was required to fit the light charged particle spectra obtained from neon on carbon, and whereas less value of R0 was required to fit for neon plus aluminum reaction. So nature of deformation and high excitation energy was also studied through GDR splitting, and here also for sulfur 32 extended product shape was verified through GDR splitting study. So this is a very good experiment where from 3 different probes we can establish that this neon and carbon system forms a very large deformed shape. So in fission studies, what we are pursuing at BCC, we study cell effect in nuclei, at fast excitation energy, cell effect versus out. We study fission and deep sub-barrier energies, fission cross-section measured in third harmonic of cyclotron and deep sub-barrier energy of 7.7 MeV. No measurements have been reported so far, and we are exploring the fission dynamics. Moreover, we have studied physics related to super-heavy elements. So, in nuclear fission studies, we have observed the direct observation of washout of cell effect. So, to constrain the excitation energy at which nuclear cell effect vanishes, fission fragment mass distribution are measured at wide excitation energy range, and from 21 to 64.2 MeV, and you see the shape of the mass distribution changes from symmetric to asymmetric as we go down to lower excitation energy, and around 40 point nuclear shell effect washes out excitation energy of 40 MeV in U236 MeV, U236. So we also measure the fission time scale. Atomic method for fission time, anomaly still exists between the fission time scale measured by nuclear and atomic technique. So time scale measured using K-X-ray technique for fission of plutonium produced in alpha uranium-238. Width of the line is a measure of time scale, and we observed narrow peak at 102.8 keV corresponding to plutonium X-ray indicates the fission time scale is of the order of greater than 1 in 10⁻⁻18 seconds. So another area where we are working is studies of GDR using lambda. So GDR is a small amplitude, high frequency collective mode of excitation in nuclear. So we studied the study of dependence of GDR width at high temperature, proving clustering phenomena in atomic nuclei using GDR as a tool, Jacobi set transition, systematic study of isospin mixing, fluidity of finite nuclear matter. So these are some of the related publications, recent publications. So one of the very important experiment was carried out where eta by S of finite nuclear matter have been measured. The fundamental quantity of the ratio of shear viscosity to entropy density gives a measure of the fluidity of the matter. The smaller the eta by S, larger is the fluidity. The value of eta by S, the ratio of shear viscosity and entropy density is closely similar for strongly correlated system like KGP. What is its value in finite nuclear matter? How can it be determined? Done in VCC for the first time. Eta was determined from Libya and S entropy density was determined from Newton evaporation study. Four systems were studied and eta by was, for all these four systems, eta was increasing, S was increasing, however, eta by S was found to be within 2.5 to 6.58 by 4 kb in all cases. The measured eta by S values are comparable to that of high temperature plasma, pointing towards the fact that strong fluidity may be the universal feature of the strong interaction of many body quantum systems. These results have been published in PRL. Now, another area where we are studying nuclear level density parameter and its dependence. The dependence of level density parameter A or its inverse K on angular momentum, temperature, nuclear cell structure, isospin has been studied in detail. So this is the excitation energy and angular momentum. This is a typical experimental setup, and this is the excitation energy and angular momentum dependence, effect of cell structure and nuclear level density, isospin dependence in nuclear level density. We have seen that the reduction of level density as we move away from beta stability line. So these are some of the publications. Another important things we have observed is direct experimental signature for collective enhancement in nuclear level density. You see, for the rotational means deformed nucleus, intrinsic level, the level density has got two parts. One is single particle level density, intrinsic one, and another is the collective enhancement factor. So these collective enhancement factor dies out at high energy and K collective becomes one. So direct experimental signature was missing. So we did an experiment where we studied two deformed system and another spherical system and measured the neutron energy spectra at different excitation energy in small gap. And we found that for the deformed system, K inverse means inverse of level density parameter decreases with excitation energy, that means which means that level density parameter increases for this which is a direct experimental evidence for collective enhancement in nuclear level density. So nuclear temperature also showed a sharp increase at this region. So abrupt variation in apparent temperature for the two deformed system have been seen, whereas for the spherical system there is very little variation is seen. So this is the first direct observation of collective enhancement of nuclear level density and its linkage with deformed to spherical shaped phase transition in nuclear. So these things have also been verified using GDR experiment where there is an enhancement have been collective enhancement has been seen for GDR spectra also. Nuclear structure studies. So nuclear structure studies, so we mainly study in-beam spectroscopy, decay gamma spectroscopy, level lifetime measurement, change in decay rate study. So this is the nuclear chart, and you see from we studied the properties of nuclei at different region, but mostly they are near to the stability line. So the type of experiments we have carried out to see the safe evolution and effect of high orbital in nuclear near spherical nuclei around the cell closure, realization of a higher order shapes and symmetries in mid-shell nuclei, manifestation of triaxial shapes in transitional nuclei, environmental effects on beta and gamma, beta and alpha decay rates in nuclei. So these are the very recent publications obtained from this nuclear structure studies. So I will come to one recent study, the observation of exotic mode of excitation oblique in 183 gold. So this is the only 10th nucleus about 3000 known nucleus for which oblique phenomena has been identified. Uniqueness in the 183 gold is that only instance in which multiple transverse oblique bands in the same nucleus has been identified. Two different behaviors of oblique energy with spin, both increase and decrease, have been observed for the first time. Only nucleus in which the transverse oblique energy increases with the spin. So the experiment was carried out at VCC using Inga facility and using neon beam. And you see that this is the two transverse oblique band. So for one band, so there is an increase of oblique energy with spin. This is a new phenomena, and generally oblique energy decreases with spin was known. So a new concept IM was introduced for RE less than IM, oblique energy increases, and for I greater than IM, oblique energy decreases with spin. So this work has been published in PRL recently. Our recent study on the Hoyle state of carbon. So let me tell you what is Hoyle state and its importance. I'll little elaborate this study. So enormous experimental and theoretical efforts have been devoted in the last few decades and still going on to understand the precise nature of the element carbon. This element is the backbone for the existence of life on the Earth. It is also crucial for formation of all the observed heavier elements in the stellar environment. So Big Bang nucleosynthesis, Big Bang theory predicts that when the universe was formed, the only matter that existed was the hydrogen, helium, and very tiny amounts of lithium. If this is true, then all other elements must have been created in the structure. So elemental abundance in the inverse fact is that hydrogen and helium are the most abundant in inverse, 75% hydrogen and 25% helium. So carbon is the fourth most abundant element in the universe. Now the question is how other elements how they are formed. So after in the stellar nucleosynthesis, after the PP chain, so you one get the alpha nucleus, with the helium nucleus. After that, it was difficult to proceed fusion beyond helium. So if you see helium fuses with neutron, helium 5, it decays within 10 to the power minus 22 seconds. Helium, if it combines with protons, so the lithium 5, it will decay.